Dear students, in this lecture we will talk about crystal system and Bravais lattices. There are 7 basic crystal systems and 14 Bravais lattices. These crystal systems and Bravais lattices are classified on the basis of symmetry. Bravais lattices are basically the unit cell of crystals. These are defined by 6 parameters. The first 3 parameters, which are the length, which are called as A, B and C, and 3 interaxial angle that are alpha, beta and gamma. So these 6 parameters that are the 3 axes A, B and C and 3 interaxial angle alpha, beta and gamma define the crystal system and Bravais lattices. Now let's explain 7 crystal systems and their Bravais lattices. First of all, we will discuss the simple cubic crystal system. So this one is the simple cube. This one and these corner points, which are called as the lattice point of this cube. So this is the lattice, cubic lattice. So when we bring the atom to these lattices, which are also called as bases or motifs, as we have already discussed in our previous lectures. When we combine the atom to these lattices, so these are the 8 corners, 8 lattice points, and when we combine these lattice points with the atoms, it becomes the cubic crystals. So this is the cubic crystals. These cubic crystals, when we take this point as reference point, it has the 3 axes. So, and these are the angles between them. This is the angle alpha, which we define in this structure. It will be here. This is the angle alpha between these 2 axes. This one is the angle beta. In structure, it will be defined by this point. As we are taking this point as our reference point, so this will be angle alpha, which is between this one axis and this one axis, and this one will be angle beta, which is between these 2 axes, and this one is our angle gamma, and these are the axes A, B and C. This one is the A, this axis is B, and this axis is called as C. So in this structure, all 3 axes have equal length. That is, A is equal to B is equal to C. All 3 axes are equal in the cubic crystal structures, and all angles, that is angle alpha, beta and gamma, are 90 degrees. That is angle alpha and angle beta, which are the exterior angle, and this one is the angle gamma, which is the interior angle between 2 interior axes. All these angles are of 90 degrees. This is the simple cubic structure. Here, now we will discuss the simple tetragonal crystal systems. This is the crystal lattice. This is the lattice. These are the lattice point. Lattice points are at the corner of this tetragonal system. These are the lattice point. This is the simple crystal lattice, tetragonal lattice. Now, when we bring the atom to these lattice point, like this one, this is the atom. This one atom is to this lattice point. This goes to this lattice point. So it has the 8 lattice point. So we bring the 8 atom to these lattice points. So it has 8 corner and 8 atom at or attached to these lattice point. This is our simple tetragonal crystal system. Again, it has a 3 length, this one, and this one length. We take this atom as our reference point. So this is the length A. This one is called as length A. This is our length B, and this will be our C axis. So when we take this point as our reference point, this is A, this one is B, this one is C. So B and this axis is called as C axis. Now this one is angle alpha, which is between B and C. This will be angle alpha, and this will be angle beta, which is between A and C, and this one is the interior angle, which is between A and B. Here you can see in this structure that unlike the simple cubic structure in which the all axes are of equal length, here you can see that A and B are of equal length, but both these are not equal to C, as C is elongated, that is, it has more length than A and B. It is longer than A and B. So A is equal to B, and both these are not equal to C. Although the lengths or axes are not equal, all 3 axes are not equal to each other, but the angles are still of 90 degree. That is, angle alpha is equal to angle beta is equal to angle gamma are equal to 90 degree. So this is our simple tetragonal crystal system. Now we discuss the simple rhombohedral or trigonal crystal system. This is the simple lattice of rhombohedral or trigonal crystal systems. It has the lattice point at the corner of this rhombohedral, like this one is our lattice point, this one. So all these corners have the lattice point. Now we bring the atom to these lattice points. Like this atom goes to this lattice point, this one is here, this atom goes to this lattice point, this goes to this one. So in this way we bring the atom to each lattice point. So there are 8 atoms at each corner of this rhombohedral or trigonal crystal system. Now this is called as the rhombohedral crystal systems. So this crystal system, which is a combination of lattice and atom. So it has 3 sides, that is, this one is the A axis, this is our B axis, and this one is C axis. Now again we take this atom as our origin, this point as our origin, like this one. So this is our A axis, so this is our B, and this one is our C axis. In this structure, this will be equal to this one, and this one. So now we discuss the angles. This one is the angle alpha, which is between B and C. This is angle beta, which is between A and C. Angle gamma, which is between A and B. So here you can see that all 3 sides are equal length, that is, all 3 axes are of equal length, that is, A is equal to B is equal to C, but their angles are not equal to each other. Angle alpha is equal to angle beta, but angle gamma is of greater length, is larger than alpha and beta. So these angles are not equal to 90 degree. So alpha is equal to beta is equal to gamma are not equal to 90 degree. These are different than 90 degree. So this is our rhombohedral crystal system or trigonal crystal systems. Now we discuss another crystal system, which is called a simple orthorhombic crystal systems. This is our orthorhombic lattice. That is, it has a lattice point again at corner, so which is different than simple cubic structure. When we bring the atom to this lattice, like this one, we bring the atom at 8 corner, at every corner of this simple orthorhombic. Now it becomes the orthorhombic crystal, which is the combination of lattice plus atom. And now these are the axes. This one is our A axis, this one is our B axis, and this one is C axis. This one is C axis. Now this is the angle alpha, which is presented here. This is angle alpha, this one is angle beta, and this one is angle gamma. Now here you can see that all sides are different. That is, A not is equal to B, not is equal to C. All axes are of different length. A not is equal to B, not is equal to C. But their angles are still of 90 degree. That is, angle alpha is equal to angle beta is equal to angle gamma. All angles are of 90 degree. So this is our simple orthorhombic crystal system in which lengths or axes are not equal to each other. All are of different length, but their interaxial angles are still of 90 degree. Now we discuss the simple monoclinic crystal system, which has the least symmetry, second least symmetric structure. This is the simple monoclinic lattice. Now we bring the atom to this monoclinic lattice. Now this atom goes to this point, this one, this one, this one. In the same way, we bring the atom to each corner of this monoclinic lattice. Now it becomes the monoclinic crystal. This is the crystal of monoclinic crystal systems. This one is length A, this is length B, and this one is length C. Now again we take this point as our origin. So this is A axis, this is one is C axis, which is in this structure. This is equal to this one, and their angle is alpha, beta, and gamma. So this is our angle alpha, which is between C and B, which is angle beta, which is between C and A, the angle gamma, which is between A and B. Here you can see that again all three lengths are of different from each other. That is, length A axis not equal to B, which is not equal to C axis. In the same way, angle alpha and gamma are 90 degree. Here you can see that this one angle and this one angle are 90 degree, but this angle is different than 90 degree. That is, angle beta is not equal to 90 degree. So this structure is the second least symmetric structure. It has the least symmetry. So this is our monoclinic crystal system. Now we discuss the simple triclinic crystal system. This is our triclinic lattice. This is our least symmetric crystal structures. So this is the lattice. Now we bring the atom to this lattice points. In this way, each corner lattice point has the atom. Now it becomes the triclinic crystal systems. So this is length A axis, this is B axis, and this one is C axis. If we take this point as our origin, so A, C, and now we discuss the angle. This is angle alpha, this is angle beta, and this one is angle gamma. So as this structure has the least symmetric structure, this is the most distorted crystal structure. So all lengths are unequal to each other, that is A not is equal to B not is equal to C. In the same way, all angles are different from each other and different than 90 degree, that is angle alpha not is equal to beta not is equal to gamma. All these angles are not equal to 90 degree. These are the different than 90 degrees, so it's the most distorted crystal systems. Now we discuss the hexagonal crystal system. Here you can see that this is the hexagonal crystal lattice, and here you can see that it has the 6 axes. This one, 2, this 3, 4, 5, and 6. This one is the hexagon on the top and hexagon at the bottom. So this is the hexagonal structure. It has the two its units. Cell has the 2 hexagon at the top and at the bottom. Now we bring the atom to this hexagonal lattice. So it has the atom at each corner of the hexagon as well, and the atom at the center of hexagon. In the same way, in the bottom hexagon we have the atom at each hexagon side, at 6 sides and at the center of this hexagon. So this is our hexagonal crystal system, which has the atom, 6 atoms at the corner of hexagon, 1 at the top and 1 at the bottom, and 1 atom at the center of each hexagon. So here you can see that if we take over this point as our origin, this one is the side A, this one is the side C, that is the smaller side. This is the smaller side and this one is the larger side. Larger axis or larger side. This is the angle alpha, beta, and this one is angle gamma. So here you can see that A is equal to B, which is not equal to C. So this A side and B side, both these lengths are equal. Actually, the all lengths or these hexagons are equal. This is equal to this one, this one, this one. All sides are equal to each other. But these are not equal to this larger side. This C axis is larger, which is combining both these hexagon. This is the larger axis. So A is equal to B, which is not equal to C. C is longer than A and B. So here you can see that angle alpha and angle beta, which is between A and C, and B and C. Angle alpha, which is equal to B and C. Both these angles are equal to each other. But angle gamma, which is between A and B, which is the interior angle, which in structure it will be here. This angle is larger than 90 degree and it is equal to 120 degree. So this one is this one angle. This is the 90 degree, but these exterior angle, which are the angle alpha, which is between B and C, A and C, both these angle are of 90 degree. So this is our hexagonal crystal system. On the basis of symmetry, there are 7 crystal systems which can be subdivided into 17 Bravais lattices. And this one is the classification of crystal system and the Bravais lattices. Here we have the crystal system and these are the Bravais lattices. We have basically the 4 type of Bravais lattices, like the primitive Bravais lattices, face-centered, FCC, or it can be represented by simple F. And then we have the body-centered BCC, it can be represented by I, or we have the base-centered, which is called as can be represented by AB or C. So first of all, we discuss the Bravais lattices of cubic crystal system. In cubic crystal systems, we have the 3 type of Bravais lattices: primitive Bravais lattices, face-centered, or body-centered. In primitive Bravais lattice, which is represented by P, in primitive Bravais lattice we have the atom only at the corner of cube. That is, we have the 8 corner of cube and we have the 8 atom at each corner of cube. This will be the primitive Bravais lattice. And then we have the face-centered Bravais lattice. In face-centered Bravais lattice, we have the atom at the corner of cube, and other than the corner atom, we have the atom at the center of each face of cube. That is, so we have the 6 more atom at the center of 6 faces of cubic crystal system. So this will be our face-centered Bravais lattice, which is the atom at the corner and atom at each face of cubic crystal system. And then there is another type of Bravais lattice which is called as body-centered Bravais lattice. In body-centered Bravais lattice, we have the atom at the corner of the cube and one atom at the center of cube. So there is one more atom at the center other than the 8 corner atom. This will be body-centered cubic and it can be represented by I. So simple cubic crystal system have the 3 type of Bravais lattice, which are P, F and I. Now comes to the tetragonal crystal system. Tetragonal crystal systems are the 2 type of Bravais lattice. Number 1, that is the primitive Bravais lattice, in which it has the tetragonal crystals have the atom only at the corner of tetragon. And then there is the body-centered crystal tetragonal crystal system, which has the atom at the center of tetragonal crystal system other than the corner atom. And then we have the hexagonal crystal structure, which have the only primitive Bravais lattice. And then rhombohedral crystal structure, which also has only the rhombohedral Bravais lattice. There is no face-centered, body-centered or base-centered Bravais lattice for these crystal systems. And then there is orthorhombic. Orthorhombic crystal structure which has all 4 type of Bravais lattice. That is primitive, face-centered, body-centered and base-centered. That is, now we discuss the base-centered. In base-centered Bravais lattice, orthorhombic Bravais lattice, which has the atom at the corner of orthorhombic and then atom at the base. Or at for it depends on the position of base centered. It can be either of A type, B type or C type. It can have the atom at the top or bottom face, or it can have the atom on the two opposite faces, or it can have the atoms on the front face and on the face behind the front face. That is, it depends on the position of base centered atom. It can be of either A type, B type or C type. So orthorhombic crystal systems have the A type base centered crystal system Bravais lattice, and monoclinic crystal system which also have the primitive Bravais lattice and base type A type base centered Bravais lattice. And now we come to the triclinic crystal system. Triclinic crystal systems have only primitive Bravais lattice. So if we count all these Bravais lattice, so we have 14 basic Bravais lattice within the 7 crystal system. So these are the 14 Bravais lattice and 7 crystal system, which are classified on the basis of symmetry of crystal.